Mm. Ah,
No comments, right? No, sin commentari. No?
hello, I'm back again because I don't see any of your videos, so that's okay.
Professor Jody, you want to show your PPT PowerPoint?
Yes, I am going to do it now. Yeah.
Yeah, you have to check, I think. Yes, it's.
Are you able to see something? Yes?
Yes, yes.
Okay. Okay. I will stop.
Yes, whenever you need the graphic, we can start. Am auzit la telefon, am nevoie de răspuns până mâine.
Okay. Hello. Am I audible? Okay. Okay, welcome to everyone to this workshop. This is it will be a good thing to participate in this workshop because it will give collaboration between industries, professors, experts, and many universities from the European Union. And this workshop is like for discussing idea and background information and future research trends about IoT and IoT devices. So first of all, I want to introduce myself. I am Raviraj. I am from Universitat Politècnica Catalonia, from Manresa campus. I am working as a visiting professor in the Merit project. My area of research background is from artificial intelligence, especially in the field of computer vision for the robotics applications. I recently started my job here in Manresa. Before that, I was working as an assistant professor in the Institute of Robotics and Machine Intelligence in the Politechnika Poznanska, Poland. So first of all, I am going to invite the first keynote speaker of this workshop, who is Professor Radu Buneca from Romania. Could you please start your presentation?
Okay, thank you. So I will start to present, right? At this
Yeah.
point. Okay, just a second. Okay. Okay, just a second. Do you see my screen? No.
We saw it for 3 seconds.
Okay. Okay. Do you see my screen?
Yes, yes.
Okay. So hello everyone. So my name is Radu Bonca, and I lead the complex system engineering department at the ICI Bucharest, which is a research institute in informatics in Romania. Today I'd like to share some insights into our journey, let's say, of setting up our IoT and robotics innovation labs. I walk you through a few of our key projects that highlight the strategic areas we are focusing on, areas we believe are highly relevant for the future of this domain. And I will outline some of the core challenges we are currently faced as a research and innovation hub. It's important to mention that within our strategy, institutional strategy, IoT is not treated as in isolation. It's deeply intertwined with robotics and artificial intelligence. So basically, we treat all these three domains as one larger innovation hub. So our work is basically driven by the convergence of these three technologies. So our innovation labs were launched in 2022 with the ambition to become, by the end of this year, a fully operational hub, offering services such as test before investment, mentorship and talent development, technology transfer, and innovation brokerage. Our focus areas span across IoT, robotics, like I said, artificial intelligence, security, cybersecurity, blockchain, digital forensic, and immersive technology. These are all the labs. Each lab typically consists of like a compact agile team for each lab, up to 5 or 6 members. We are very young. Our current average age is just 28 years old, so quite young, reflecting basically our commitment to nurturing this young talent. So many of our member teams are students, master graduates, PhD candidates, and so on. About our value and technology stack, basically we cover each member has extensive knowledge to cover all the layers. So from data science, machine learning, several programming languages, including how to know how to make applications, databases, to run operations and integration pipelines. And of course, specifically for this domain, has to know the IoT and edge computing technologies. So our values is we actively embrace the convergence of hardware, software, and data science. Another value is open innovation. We contribute and build upon open source ecosystems. We share modular tools. We annotate data sets, and we publish, for instance, in GitHub. One core value is rapid prototyping and agility. In fact, we encourage this mindset of fail fast, learn faster. We are driven by data-driven excellence, and we encourage curiosity and lifelong learning. A little bit about our setup, about our infrastructure. Basically, each lab, we built a unified lab that brings together IoT, IE, and robotics, for instance. It's one big lab. And they share the same infrastructure and the same leadership. In this case, it's me. So the lab supports the full innovation cycles from idea exploration, proof of concepts, prototype development, and technology transfer. So our infrastructure includes locally a self-managed hyperconvergent setup with, for instance, GPU servers and Intel NUC-based nodes, a layer of virtualization like Proxmox, Docker Swarm. Then it's the next layer of let's say, where we put applications, for instance, PostgreSQL or databases, data processing pipelines, and Jupyter Hub, Isaac Sim, ThinkSport, things that are used both in robotics, IoT, and artificial intelligence. So typically, this is what like a typical homepage looks like in our lab environment. So each team member can customize their own dashboard with quick access to the tools they use most. All tools are containerized, ensuring flexibility and isolation. If a tool isn't available by default, researcher can install the tool by themselves, either in their personal workspace, within their team environment, or even system-wide if they have sufficient permissions. So this setup encourages autonomy while maintaining a collaborative, secure, and scalable environment. I will go with examples of application that we made. So this is our robotic research platform called OpenBot Waffle, which has been designed and built by us from the ground up. Just a second, because I'm not sure if it has been built up from the ground up. It's open source. It has been published on GitHub, including all the 3D printing models, the robotic operating system modules, and plenty of examples to get started with standard tasks in robotics. Such as standard tasks. I mean, by standard tasks, tasks like localization, pathfinding, teleoperation, etc. We have a digital twin in Gazebo, which is a simulator used in robotics, and we're working now on developing the package, the package for NVIDIA ISAC-Sim, which basically is the most used simulator on the market. And we have received actually good feedback on Twitter from Open Robotics. These are the guys that maintain a robotic operating system. So why did we develop this robot in the first place? Well, for once, we wanted something relatively cheaper than, for instance, playing with Google Aloha, which costs around $35,000. For reference, our robot gets around $800. And secondly, we needed to understand the robot at deeper level so that we would be able to modify it depending on incoming requirements. Our current use includes autonomous navigation and planning, which is already implemented. That is to tell the robot go from lab 1 to find to lab 2, find a pen on the floor, I don't know, bring it to lab 3, put it on the floor, and then return to lab 1. So this is kind of task, autonomous navigation and planning. Another use is artificial embodiment, and this is where IoT comes in place, where the robot has access to different sensors, or more specifically, it has access as a toolkit to IoT platforms, where the data coming from different sensors reside. So just to give you an example, for instance, we have webcams deployed all around our labs, like Raspberry-based webcams, and we have an application that is logging each person where it is. It's running a small local model for identifying the people, and it writes each person where it is at what time. And the robot has access to this journal, and if you ask the robot, go find Radu, for instance, it will know where Radu is and will go to his location. We also use this robot for experiments such as using visual language action models and reinforced learning. Oh, sorry, I forgot something to say about the robot. It's not just for research. We are also exploring right now real-world use potential for industrial beneficiaries. Currently, we are in discussion, for instance, with several hospitals to pilot a larger version of this robot, like a working cabinet, to automate the process of delivering food to the patient. So we are working on identifying a suitable hospital environment, ideally one with features like automatic doors and unobstructed floors, as the robot requires a smooth, accessible accessible layout. This is how we imagine our robot, like in the left, our robot hero cleaning the world. This will be ideal task that robot could do. And in the right, if I play the movie, it's what actually in reality usually happens. So it's a lot of iterations to make it work. Here in this case, these are generated with AI, so just to make clear. But usually things don't work from the start. So this one challenge we have. Okay, this is a project that we currently are pushing. It's quite a big project we are involved with. This is okay. This is one of the strategic initiatives. Let's say we are currently involved in collaboration with over 12 Romanian partners, including the Institute of Geophysics, Geology, Speology, Constanța Harbor, a mining company, for instance, Romanian Academy, and many other smaller companies. The main objective is to fuse all the data sets that are already being collected independently from in earth science. These data sets include the seismic and microseismic data from an extensive distributed acoustic sensor network that Romania has, data sets regarding gas emissions that are monitored in natural environments such as caves, urban microseismic activity, satellite imagery, and earth tomography data. And fusing such heterogeneous data streams is a major challenge to ensure reliable analysis. All data must be timestamped and synchronized. So this is one project that we have, and of course, consolidating all this data set into a larger one to run correlation and causality analysis, outlier detection. So the motivation is strong because Romania faces is one of the let's say environments in Europe where there are three colliding things like major earthquakes, major floods, and major landslides. A little bit about IoT trends. This slide says the projected evolution, let's say, of IoT and its convergence with AI and robotics as we see it from 2022, where there was the AI tipping point to 2035, along two key dimensions, technology complexity and societal impact. Until 2022, IoT applications were mostly cloud-centric and limited in intelligence, focused on basic monitoring, dashboards, and system viability. But now, by 2030, we expect a shift towards edge and fog computing. Now, this is not the research; it's just in the real use cases. So, hyperconnectivity, system becoming more context-aware, human-centric, and tightly integrated with robotics and high-level automations. Looking ahead to 2035, we will have swarm robotics, cognitive intent-aware system, integration on multi-dimension, multi-domains like biology, material science, and even off-planet IoT ecosystems. So challenges, we have input challenges, process challenges, and output challenges, let's say. So and on the input side, talent retention, skill development, it's quite a growing issue, especially in this competitive tech landscape in general in Europe. It's a problem. The second would be funding volatility. We rely heavy on project-based funding instead of strategic, let's say, a long-term finance, which makes long-term planning difficult. And sustaining infrastructure is another challenge we have here. As for the process challenges, the barriers we encounter are fragmented ecosystems, which makes coordination across academia industry quite difficult, regulatory and ethical complexity, open science versus data sensitivity, especially in Europe with all the regulations. And the output, it's a challenge is bridging research and market adoptions, and technology transfer and commercialization. So this basically affects the systemic barriers innovation labs like ours must overcome, which I presume it's basically general to Europe. So that would be the presentation. Thank you. I guess, okay, I'm in time, I guess. Thank you, guys. Questions? I'm not sure if the questions come later or now.
Thank you for your presentation. Your presentation is moreover related to robotics. It was nice.
So
I
maybe
am
we
invited.
we
some
can move
questions.
over with the presentations. Please note your
Okay.
questions, and afterwards of when we finish with the presentation, all the speakers will be available to take questions from.
Okay. So I am inviting Mr. Lucian Alexa.
Thank
He is
you.
the next speaker. Okay.
I'm sharing now. I hope you see it.
Yes.
Okay. So I'm an IT expert from Northeast Romania. We are, okay, let's see also. We are a non and also governmental organization. It's a new status for us because now we're managing authority for the regional program for the Northeast. So our status is highly diversified, let's say. We're non-profit, we're for the public utility, and we're trying to reduce the regional disparities by developing the northeast of Romania. It's not about IoT only. We are trying different ways to digitalize, and we're supporting SMEs and also local authorities to develop, to expand, to seek out new technologies and possibilities. So we had several initiatives. This is one of them. So there are too many to actually announce it because it would take me a few minutes, let's say. But these are one of those. Regarding to the help provided in the region, we had the call. Usually such help, let's say, is called a call. We had 3,000 applying companies. Some of them answered our questionnaires. They passed the process of being selected, and then they applied. 350 actually received fundings, which are up to 100,000 euros per every SME, and the total is 32 millions. This call is in progress, so it's actually working right now. Also, for the administrative units, for the local administration, we are trying to, I don't know, move them to the next century. And we ran some questionnaires asking them what they need, what they have, how do they see the world that is coming. So we identified several of their requests. Most of them, this is the actual order of the actual report. The number one was integrated video surveillance systems with centralized command centers. This is also a core function for IoT because they require real-time data streams, smart analytics, and not to mention the network of the sensors or networks if you have many. Also, we are going to need utility infrastructure for monitoring systems. They need to make, I don't know, predictions in telemetry and SCADA type systems in order, for example, to track water, energy, waste infrastructures. We are going to need reporting for the problems, environmental or other sort, air quality, illegal dumping, in an easy manner from a mobile phone, for example, from an app, or maybe automatically, I don't know, report problems. Also, they need the social services monitoring for the oldest people, for the vulnerable population. They can wear IoT stuff and receive instant access or, I don't know, attention. I know that in some zones, this is already in place. Sometimes even for a remote consultation. The cities also asked for smart parking systems, and IoT can help with real-time space detection. Payment, we always need easy access to payment, not to sit around and wait, but have it easily available. However, we also saw that they are not really prepared for this change because they lack firewalls, centralized management, 30% even lack basic protection. They only have a router which is open, it's basic firmware, it's not protected at all. So this has to be addressed. They lack on-premise servers, and they usually have one server which, if it breaks, nothing is available anymore. So we have to build a resilient infrastructure for that. Their maps are fragmented, so they need GIS data systems. Sometimes this can be solved. Sometimes you have to invest in it, and IoT can help. And in some zones, there is an absolute absence of public service digitalization. Sometimes paper is the only way to do stuff. So we are proposing some solutions. A GIS for urban planning as a platform to integrate sensor data, that is environmental monitoring, utility networks, as a platform or several platforms for smart social services. Those can be used by IoT wearables or some other solutions. We can have data-driven systems. Those are AI or machine learning systems that can learn from the networks of the sensors. Traffic cameras or parking or public transportation. we proposed smart parking and traffic, which can be seen centralized. And of course, platforms for reporting incidents, some automatic, some from the users. This is the proposal, and I don't know, the top priorities for our urban cities. And this is the moment to apply and change the way we see our own future. We have problems, challenges, let's say, cybersecurity gaps, missing or weak infrastructure, some systems that are fragmented, they're not connected to each other. Each one solves the thing, but only for a small region, for example. And we have some urban zones which are completely undeveloped. So they can't have any tech right now. But this is going to be taken care of. So these are the calls for the cities, and they are now on display. They are. This is the moment to apply for this. This is the problem for Northeast region. This is the dashboard, let's say. We have several solutions, and some of them are already implemented. So I will give you two case studies, one from Orange and the other from Octavic. Orange implemented a sensor IE, and it's better, I guess, to give you the video.
Vehiculele moderne beneficiază deja de dotări pentru asistența șoferului, ce fac condusul mai sigur și mai confortabil. Participanții la trafic, precum pietonii și bicicliștii, pot beneficia de aceste avantaje doar dacă pot fi detectați de senzorii vehiculului. Provocarea rezultată poate fi adresată prin utilizarea unor tehnologii deja existente pe vehicule și integrarea lor în infrastructura rutieră. Astfel, prin Orange Business Services asigurăm conectivitatea pentru un scenariu de tip intersecție inteligentă, dezvoltat de partenerul Continental Automotive România, alături de Universitatea Tehnică Gheorghe Asachi din Iași, cu susținerea Primăriei Municipiului Iași. Împreună implementăm proiectul Smart Intersection, ce combină prelucrarea imaginilor video asistată de inteligență artificială cu beneficiile aduse de conexiunea la o rețea 5G și o soluție de tip Edge Computing.
La nivelul intersecției Podul Roș din Iași, au fost amplasate camere video de rezoluție înaltă pe 2 stâlpi de semaforizare, folosite pentru detectarea participanților la trafic și crearea unui model digital dinamic al intersecției. Pe baza acestui model, se pot dezvolta diferite aplicații, precum cea pentru identificarea potențialelor incidente în trafic sau cea de protecție a participanților vulnerabili din trafic, precum pietonii și bicicliștii.
Soluția Smart Intersection are ca scop principal dezvoltarea de sisteme care permit vehiculelor automate și conectate să-și coordoneze comportamentul de conducere atunci când trec prin intersecții inteligente. Coordonarea se bazează nu doar pe inteligența internă a vehiculului, ci și pe comunicarea cu alte vehicule, precum și cu infrastructura inteligentă bazată pe tehnologii de conectivitate precum 5G.
Dezvoltarea Orange 5G Lab Iași vine ca o completare firească a colaborării foarte bune cu Universitatea Tehnică Gheorghe Asachi din Iași și Continental Automotive România. Laboratorul are ca scop accelerarea ritmului de dezvoltare pentru soluții inovative și permite accesul la o infrastructură tehnică capabilă, disponibilă într-un nou data center bazat pe tehnologii de ultimă generație. Arhitectura soluției Smart Intersection are la bază această infrastructură și conectivitatea 5G.
Tehnologia 5G 5G furnizată de Orange contribuie la îmbunătățirea substanțială a soluției Smart Intersection prin 3 caracteristici specifice conectivității de ultimă generație: latența ultra scăzută și fiabilitatea ultra înaltă, densitatea mare de conexiuni și capacitatea de a transfera un volum mare de date și estimarea foarte precisă a poziției utilizatorilor mobili oferită de serviciile de localizare 5G, care ajută la îmbunătățirea siguranței participanților vulnerabili din trafic.
Proiectul prin care a fost dezvoltată intersecția inteligentă din Iași demonstrează încă o dată cât de important este obiectivul companiei noastre Continental Automotive România. Obiectivul Vision Zero înseamnă 0 accidente fatale, 0 accidente cu victime și 0 incidente în trafic. Acest deziderat este foarte important pentru România, având în vedere faptul că în cursul anului 2021 s-au înregistrat aproximativ 27.000 de accidente de circulație rutieră la nivel național, rezultând un număr de peste 35.000 de persoane accidentate, dintre care 5% persoane accidentate mortal. Conform studiilor realizate și a previziunilor făcute de instituțiile avizate, numărul persoanelor accidentate în România s-ar fi putut reduce cu 10.500 de persoane dacă ar fi fost utilizate sisteme de trafic inteligent care să folosească tehnologii moderne, precum cele implementate de noi în Iași.
Această soluție presupune, deci, digitizarea modului în care funcționează intersecțiile în orașele viitorului, precum și sporirea siguranței în trafic. Mai mult, acest use case reprezintă doar o mică parte din aplicațiile industriale și comerciale ce pot fi dezvoltate cu ajutorul tehnologiei 5G.
Okay, this is a project already in place. Also, Octavic is implemented.
In today's fast-paced and highly competitive industrial manufacturing world, factories often struggle to collect and analyze critical data in real time, making it difficult to understand the efficiency of their production processes and losing hundreds of hours with repetitive tasks like manually building reports. Without a complete view of the factory's shop floor, optimizing operations and making data-driven decisions becomes an impossible task for decision makers in production. And that's the vision that drove us to develop Octavic, our digital manufacturing operations management system. It's a complete solution that enables you to gain operational visibility and design improvements to the entire production process from end to end. But let's take a look at your factory's digital journey with Octavic. We first start by collecting real-time data from all your production equipment, integrating them seamlessly into our visual management boards, tailored for each organizational level. Therefore, you gain operational visibility into everything that happens in your factory, wherever you are, whenever you want. Using our automated reporting, our customers save hundreds of hours every month of manual data collection and reporting. Using and-on alerts, Octavic instantly notifies you and all the relevant stakeholders whenever production issues arise, drastically reducing reaction time and waste, keeping your operations running smoothly. You'll never have to speculate on how everything works anymore. With Octavic, you can monitor over 70 key performance indicators, allowing you to pinpoint production problems and target improvement actions. But that's not all. Our system also empowers you to track real-time electrical energy and industrial fluids consumption, helping you reduce your bills and save the planet. After a few months, you can even say goodbye to human error and inefficiencies in production planning. Our AI-based system generates automatic production schedules, maximizing efficiency and reducing costly mistakes by alerting whenever you might run out of materials or miss any deadlines. If you ever need any help, don't worry. You've got Ada, Octavic's AI-powered data assistant. Access information, request reports, and get real-time updates, all with simple voice commands, just like Siri, dedicated to factories. You can choose to implement the entire system or just specific modules, since the Octavic system is designed to fit your factory's specific needs. Octavic's system is being used in multiple different factories and industries across the world, helping them reach annual benefits of millions of dollars starting as early as year 1. Don't fly blind. Pilot your factory today and unlock the full potential of your production processes using the Octavic Manufacturing Operations Management System.
Okay, and they didn't provide an actual view of the interface, but here it is. We have management, we have the line, and even the operator interface with the problems that can arrive. However, Gabriel from Octavic is here with us. If you have any specific questions, feel free to ask him.
I'm the person if you need to ask anything. Thank you very much, Lucia.
Thank you.
Okay. Thank you very much for your presentation.
Thank you.
Yeah. So now I am going to invite Professor Ravishay from Tallinn University of Technology. Hello.
Hello. Let me share the screen. Okay, I hope you can see the presentation.
Yes.
So yes, thank you. Thank you for inviting. There was discussion from keynote speakers about the challenges and trends. So I'm a little bit addressing the, let's say, educational side, because we need people who really implement those IoT challenges, and then so the young people, and how to educate them that they are aware of IoT and all those issues. It's one of collaboration project between Polish, Latvian, Estonian universities. It's in the mostly educational project, not that much a research project, but still it's related to different aspects. So going to give you a 10 minutes overview about this, and I hope it's interesting. So we have or a little bit the background. Of course, everyone knows what's the IoT. Everyone is aware of industry revolutions, and IoT was one of the enabling technology for Industry 4.0. So now we are entering the Industry 5.0, and I think here the IoT is actually kind of bridging technology, and also very key technology for bringing the industry also more the human-centric, because by collecting data, analyzing data, and then based on the collected data to make a process better, and also more suitable for the humans in industry is definitely very relevant. So IoT stays as a key technology from Industry 4.0 to 5.0 anyway. So it's therefore it's very relevant. I'm talking a little bit about remote laboratories. So this is the IoT, the learning IoT. Definitely the key thing is to doing let's say hands-on practices. So it's you can't do it in theoretical way. You're just doing exercises or solving some equations, but of course you have to do the hands-on stuff by building some sensor system, connecting things and everything. However, we have a lot of online education right now. Many people prefer to learn online, and also there are different research sharing issues behind that. So there, this virtual and online and remote laboratories actually can play quite a crucial role to still enable students to do the practical things with the practical hardware or simulated environments, and get this hands-on experience even if they're online. And these attempts has been already quite old. I would say like 20 years ago. Also here at Altech, we experimented to bringing in and this online laboratory. So we used at that time the LabVIEW software, which is still also one of the key technology. And it was just interesting to see that how how we did it 20 years ago, and then what was the computing power, for example, if we talk about servers. But bit of the different terminology, of course, there are different aspects in remote education, like virtual labs, remote labs, and online labs. So it's important to understand the difference, for example, that the virtual labs are types of the labs that there is no real hardware involved. So the environment is simulated, and you can have a really fancy and nice front end, but the processes behind that, the data, what is collected, is actually simulated. So there is no real world connections in that sense. However, remote laboratories are kind of similar, so the user interface for the student can be quite the same, but it involves a real hardware. So it means that if there are sensors, so we get the real sensor readings, and if there are actuators on the side, if students make some commands or software scripts, then it's executed on a real hardware. And usually it involves the video feedback so that you can see how things are working if you're controlling something. So this is the main difference. And of course, there is hybrid versions of this. So what we have developed in jointly, it's actually a longer time collaboration already. So we have already the second generation of this platform, but it's now up and running. It's on the piloting right now in different countries, but it's the access portal to the students that they can access very different types of remote laboratories, and specifically IoT remote laboratories. It has the front end, well, mostly the programming, is it the Python or whatever languages, and not just dependent of the compiler. It has the visual verification, but also the video feedback and other command return windows. So you can get real-time feedback about your program. Just in the right side, you can see how this front end looks like in one particular lab. And there is a 3 use cases right now, let's say kind of live, which is under the piloting testing. One is in Silesian University of Technology in Poland, in South Poland, and it consists of different microcontroller controlled ports. You can see them, they are mounted in the racks, and every student can basically book a device for a certain period of time and then program it and then see how it works. And so you can book different ones and try then to program one to control another and see then on the video cameras how those nodes are actually reacting. So mostly it's built on the ESP32 and STM32 microcontrollers, but also we have AVR and other platforms what are supported. So currently there is a 32 nodes in this laboratory in particular, and then students actively using those. The second use case is in Latvia, Riga Technical University. There is a very modern new facilities. They are all equipped with sensors about the room environment, there's a temperature, humidity, and so on. And it's in that sense different is that those sensors are not educational use in the first place, but they are just for the controlling, let's say, like smart home or smart house procedures in IoT. But what's the novel, I think, is that the sensors are made available, the sensor readings are made available also for the students. So the students can use real life data in order to practice their IoT tasks and education sites. So there are very many sensors, like all the rooms equipped with those sensors, and this gives the very good basis for massive data collection. And so this is another use case which is connected to this remote lab. And third one is here at Taltech, Tallinn University of Technology. It's again a bit different. So the idea was to show the different possible online laboratories. We have one, let's say, use the medical equipment, which is pick and place robot. And this is now also connected to the internet over this platform as IoT device. And then students can remotely program this pick and place robot. It's actually equipped with a pencil, so that you can draw something on the paper, basically replicating some industrial robotic tasks. And here we actually bring together this IoT education, but also at the same time, for example, the robotic skills or practicing learning the robotic skills, and all over the internet, it's meaning remotely. So what is the benefit, of course, in terms of Industry 5.0, and then we can offer inclusive access over the remote access, so it gives opportunity to do the tasks or exercises 24/7 basically. But also we are sharing the resources, so we don't need to build up all these different kinds of labs in every university, but one university can use other resources one semester and then vice versa. So it's also the resource sharing and international collaboration, and also the direct connection with industrial applications like the smart houses and industrial robotics. So what we actually looking further is that to expand this network. So this is also project-based, or several projects behind that initiative, but we're also interested to expand this in the future technologies, including AI and others. Also the industry integration, for example, we are planning to integrate also university machinery. So we have different equipment at university, like milling machines and things, also into the system, so the student can actually get also data how those machines are used and build on some kind of applications on top of those, and also build a new human-machine interfaces for better and more human-centric collaboration with machines. And yes, so this was short overview about what we are doing together with other university. There are videos about how the system works, how to, this kind of user guide, which here is this link is provided, and I think when the slides are distributed later on, everyone can check it out. Also, there is a paper published very recently, exactly what I was just presented. So if someone has a more interest or want to read a little bit more deep into all those free use cases, then the link directs you to this published paper. So thank you very much from my side. Looking forward.
Okay, thank you very much for your nice presentation, Professor. Now I am going to invite Professor Jordi Bonet from Universitat Politècnica Catalunya.
Okay, good afternoon. Let me know if you are able to see the presentation.
Yes.
Yeah?
Yes.
Okay.
Yes.
Okay, thank you very much. So
yes, please.
Yeah, so I'm going to share some insights from applied IoT projects in industrial settings from I will say more point of view more close to the ground than some of the previous presentations. So just to start, let's see some case examples of what I'm thinking or what I'm going to talk. I'm thinking about battery-powered applications. I will divide these applications into two types. First, the low data transmission requirements. I'm thinking small payloads and low duty cycle transmission, for example, sampling the temperature every hour and sending all these temperatures just once a day. So we are just sending about 24, 48 bytes per message. And another kind of application that involves monitoring vibrations of a motor, engine, or a pump, typically 3-axis vibration measurements. And this require have higher data transmission requirements. And just to although it's out of the scope of this presentation, I would like to say that sometimes there are IoT projects with space constraints, like the one that is I'm showing in the picture below, where we have a probe that must be put in a narrow diameter borehole. The width of the PCB is 30 millimeters. Well, as you can see, the modules that are over this PCB that are inclinometer and a gyroscope, they are I think 32 millimeters. So well, maybe sometimes it's needed to sand or stripe a little these modules. So the first challenge I wanted to talk is the baseline power consumption. We usually do our projects from scratch and we build custom PCBs. Sometimes we put modules in them, but the first thing I wanted to point out is that modules with the same reference may have different power supply, and consumption in the standby mode and slim mode can change from 0.5 to 1 milliamperes. So it's something that we cannot know before buying the module, but then you have a consumption that can be the double that expected. I'm talking about a SIM module with an ESP32. We have tried to make a replica of this module, and the result gives a consumption higher than expected, 1.5 milliampere, even if extra circuit is included in this custom PCB. Well, we think that the consumption is more than expected. Sometimes PCB manufacturers cannot assure the availability of components, so you can look for another component, maybe with different power specifications, hopefully the same footprint. But this is another issue to control the baseline power consumption. So, well, I would like to say that in low duty cycle transmissions, like the applications I'm talking about, the baseline consumption may determine the average consumption of the complete of the full system. So something we'll say about this at the end. Another challenge is when we choose a data transmission protocol. Well, as it's known, during the transmission is when the system has the power at its maximum. So if the previous problem is controlled, we have solved the previous problem, then we have to focus on this other one. Here I'm going to make a comparison between a LoRaWAN protocol and a 2G cellular protocol. In two different experiments and field tests, we have proved, we have verified that the consumption of a LoRaWAN in optimal conditions is about 25 consumes 25 less energy than 2G cellular. So this is a big difference. But we can go even further when battery life is more critical than data loss. Then we can do some things like disable the acknowledgement of this protocol. This eliminates reception windows. We can even disable retransmissions when the gateway is down. This way we prevent wasting energy. Okay, we have also seen that in field tests that when the gateway after gateways out gauges the slope of the voltage battery has dramatically increased. So during these periods, we have to do something to control wasting energy. Another thing we can do is the spreading factor. It's a parameter that has more impact in consumption. Usually is controlled by the network, but well, we can do that is we can fix it in the node, and this way sometimes when the channel changes, we can lose some data, but at the end the battery life will life longer. Well, none of these propositions have any impact if we haven't solved the previous baseline consumption. Huh? Just to comment on the figure that it's here on the lower part of the slide. The green line is the baseline consumption, about 1.4 million pairs. The blue line is the consumption when the system wakes up, samples and transmits and receives. And the red line is the average consumption during this part, that it's about 70 million pairs. Okay. The third point I would like to talk is about edge computing. In the kind of application that I was saying at the beginning, vibration applications, the raw data exceeds the LoRaWAN's transmission capacity. So there are some restrictions than the number of bytes per packet and the duty cycle during the one we can use the channel that makes it impossible to send raw data in this application. So we have what we have to do is to compress this data, even if we are losing some information. We can do is obtaining temporal parameters. Typicals are the ones here shown: root mean square, peak-to-peak amplitude, crest factors, quickness, kurtosis, and some others. And we can also select some components of the DFT, so we can, for example, just focus on the fundamental frequencies and its harmonics. These parameters can be transmitted, so this way the final processing is made at the cloud, or they can be processed at the node. Okay. We have these two possibilities, but sending raw data is not possible. Well, I would like to say that some algorithms, including machine learning, can process raw data or the key parameters in the node. So we have these two alternatives. I'd like to say that I'm not very fond of. Well, let's talk to the following slide, and here I will finish my presentation, just commenting some potential solutions to these challenges. So to reduce baseline power consumption, we lack expertise in PCB design focused on standby consumption. A more straightforward approach is to use an external circuit that cuts the power of the main system. And I'm thinking of a real-time clock or a microcontroller. This way, the consumption can be reduced from milliamperes to microamperes. If we want to reduce the LoRaWAN power consumption, we have to, more than adapt, maybe is to change the LoRaWAN protocol for some specific applications. I have commented before the possibilities we have. This requires modifying the existing libraries. This is a risky approach, but we have an ongoing final project that has successfully made these modifications, and we just are expecting for the consumption results that this implies in a field test. And about edge computing implementation, well, I would like to differentiate again the two kind of of processing. We can pre-process the data and then transmit the key parameters for final cloud processing. I would say this is something called soft edge computing. And hard edge computing, the final data is performed entirely at the node, even if you use raw data or pre-processed parameter. And we have a final degree project that is currently underway, and in which we create control vibration by deliberately unbalancing the motor shaft. And the idea is to play, because we really don't have expertise in machine learning algorithms or in edge computing in general. And we want to evaluate if machine learning is really needed in terms of accuracy, hardware requirements, computing time, etc., memory. And we want just know if, well, we know we live in a world where people confuse artificial intelligence with a PID controller. So I just want to see in which application it really needs something like machine learning at what cost, and in which others trivial algorithms that can be developed with greater advantages. So here finishes my presentation. I think hopefully in time.
Okay, thank you for your presentation. Now I am going to invite Ms. Justinia Ivanova. Please. Yeah.
Hi.
Yes. Hi.
I'm
Now you
sharing,
can start.
I'm sharing my screen right now.
Okay.
Do you see my screen?
Yes, yes.
It's perfect. Thank you, Jordi, for your nice presentation. And I'm following up with the another project, which is called flow meters numbers detection with tiny machine learning. Short information about myself. I'm Justina Ivanova. I'm a computer vision researcher in Fondazione Bruno Kessler in Trento, Italy. So our research unit, OpenIoT, is involved in artificial intelligence application applied to the agricultural domain, so-called the smart agriculture field. One of the problems which exist in this field is automatic measurements of water meter during irrigation. Some flow meters measure water movements automatically, but their cost is expensive. And we would like to provide an alternative solution to this problem with tiny devices and installed web cameras. This is our schema of the proposed problem. You can see an example of flow meter on the left-hand side, and you can see the device of camera-based measurements is ESP32i. The idea is to take pictures of flow meter numbers reading in automatic mode and to detect numbers and further to send the data to the server with communication protocol. For instance, Wi-Fi, or here LoRaWAN technology. The main problem is that the object detection model should be fit in tiny devices, and the maximum memory size is around 8 megabytes of RAM. Here you can see how the software application is deployed on small devices. First of all, the device takes pictures of the flow meter, and then this different image manipulation is applied to enhance quality of the image. Furthermore, this image is used as input for object detection model, and we use 2 of the object detection models which can fit in tiny devices. And further, these models send output as objects detected in this image. Each object is a number, and for each object we have location, and we have approximately size of the object. So we use the 2 neural networks for object detection. One is FOMO, faster object, more objects. And another one is YOLA V11, which is you look only once version 11. The main difference between those two models is that the first one is a fully commercial model and the second one is a free version. Some other differences are that the former model is lighter and is faster than YOLA V11. At the same time, YOLA V11 is more accurate in detections. These models provide as an output the objects with numbers location, as I said, and the results are for the send to the server. We experimented with several tiny devices for this task. Here you can see 3 devices: ESP32i, ESP32cam, ESP32S3 vroom. The main differences between these devices are their RAM memory, capacity of SD memory, and quality of images. The largest memory is in ESP32S3 vroom, while the smallest memory is in ESP32i. Another difference is the price. The cheapest is ESP33i with the price approximately €8 per device, while ESP32S3 vroom is more expensive with around €20 per device. So we use the several existing frameworks to solve this problem. One of them is Edge Impulse, a commercial version for training object detection models for small devices. Another framework is from ESP-IDF Expressive System, and it is fully free for usage. The advantages of Edge Impulse is that it is easy to use and to deploy without necessary knowledge of the programming language. And disadvantage is that the subscription costs around €400 per month. ESP-IDF requires knowledge of C++, and it is more complex for deployment, but it is fully free. Edge Impulse has lighter and more efficient models which can be deployed on all devices, and ESP-IDF can be deployed only on ESP32S3 vroom. We collected the data set for our experiments. We took 100 images of the real flow meters numbers and further annotated these images as in a special software environment called SWAT. Each number presents a bounding box with the class showing the label of the number. Here you can see such example. Also, we annotated signs. These images are then used to measure the metrics of applied object detection models. Here you can also see SWAT environment for computer vision annotation tasks. To train the models, we generated images from numbers by randomly placing these numbers on the plate. Plate is this so-called signature where the numbers are located for flow meter. And the resulting images were augmented with rotation, shift along y-axis, brightness, and contrast. So the idea was that by generating artificial numbers on the plate, we will be able to detect these numbers on the real device. You can see some examples of images here, rotated, colored, and contrasted. So we generated 50,000 images approximately. Okay, Edge Impulse platform was used to train the model of FOMO, state-of-the-art object detection model for small devices. This model is super effective in terms of time and memory fit. The model was trained on artificially generated images, and then we tested this model on the test images. You can see an example of object detections on the right-hand side here. On the left side, I show metrics which were achieved on the test dataset. You can see that the overall accuracy was only around 40%, which is really small. At the same time, such metrics as precision, recall, and F1 score more than 60. So in general, it works well on the deployed version. But then we also trained the YOLA V11 model, and it was better in terms of accuracy. So this model is famous for object detection task, and it was successfully applied in many fields. The original model size is quite large, more than 500 megabytes. To make the model fit into device, we applied quantization. What we did, we trained the model on the generated images and then quantized the resulting model. By quantizing model, we were able to fit it in a small device of ESP32S3 room. The results of the model performance are quite accurate. Here we show metrics of mean average precision of at threshold of 5%. And you can see that minimum achieved of 80%, maximum achieved of 98%. The problem of quantization is that the model accuracy is decreasing after it. And so we used low threshold to detect objects. So for instance, you can see number 5 is detected with only 6% of probability. At the same time, number 9 is detected with 68% of probability. And this is the example of how the model detected on the real case scenario. As you can see that we also applied for flow meter original image cut, where we cut the region or where the numbers are located. So in this talk, I compared two object detection models for tiny devices, and I also showed the advantages and disadvantages of these models. If you have any questions, please contact me by email. Thank you for your attention. This is the end of my presentation.
Thank you very much for your nice presentation.
Thank you.
Now I am going to invite Ms. Martha Milan.
Hello.
The last speaker. Yeah. Hello.
Hello, good afternoon. Can you see the slides? Yeah?
Yes, yes.
Oh, okay. So I'm Marta Millán from Asoindel. Asoindel is an SME from Spain in the area of Barcelona. And just a brief introduction to understand the projects we work. We are a software engineering company, and we develop software specifically for industry in production and laboratory applications. So we are experts in test and measurement. And what we do is to develop software that normally runs over PC or over real-time hardware in order that our customers can detect if the product parts from the production are okay and they fulfill all the specifications of the design. Okay. We work in different areas. We have 4 areas of work: test and measurement, hardware in the loop for the side of simulating physical models in real time. Another work is automated test platforms. Here we operate with sequences of tests for the verification of the products in the manufacturing plant. And the fourth is advanced industrial control, where we control servo motors, hydraulic actuators, or electrical and mechanical actuators. Okay, we are very near of UPC Manresa. That's why we normally collaborate with them, the university. And today, what I will show is some applications, real projects that we have developed related to the side of IoT. That is our main area in the Merit project. Okay, as you know, there's so many years a trend on the Industry 4.0, and we are, as a Soindel, we are more in the side of the edge computing. So what we do is to provide solutions in order we get the information from the machine, the elements on equipment of the plant. That means robots, PLC systems, or also we acquire information directly from sensors, temperature, torque, parameters, encoders, whatever. When we don't get the data directly from the sensor, what we do is to get it through other equipment using industrial protocols, such as in case of automotion, can open, or other devices, Modbus, OPC, whatever we can protocol we can use, we get the information from it. And why we do this? because the customer has a need of monitoring real-time data from the industrial plant. And what we do is to get the relevant indicators of the process in order they can analyze how the production and the validation of the products are going. What we don't do, we provide all this information from the edge through another protocol or API through the cloud. What we don't do here in our applications is the cloud side, okay? We normally collaborate with other partners who implement the web or the analytics over the cloud in order to provide the OE dashboards for production and monitoring and all this. And I will show you some examples on applications that we have worked in the edge side, okay? So let's start with the first one. These are real projects that we have implemented with customers from our area. In this case, is a machine manufacturer that has built a standalone station with a collaborative robot, okay? In this case, they wanted two objectives. One, monitorize the productivity of the station. So they needed an OA dashboard with the information. And on the other side, also get the information of the status from the axis of the cobot and the servo motors and mechanisms in order to make some predictive maintenance algorithms, okay? What we do in this case is to provide the acquisition hardware and the software to connect to the PLC of the station and also to the controller of the cobot. And what we do is to get all the information and guarantee the data format and the acquisition in time in order to provide these parameters to the side of the cloud, and also the inputs data for the algorithm of predictive maintenance. Okay, we are not experts, as I will explain in the other application. We are not experts on AI or algorithms of this kind, but normally the customer knows very well his own process. So what we do is to get the data in the format that the client needs in order to get the input for these algorithms, okay? And also help them with the visualization and the reporting of the data. This other example is also on a standalone application. But in this case, the architecture is a little different because the customer wanted that we use device that is similar to a PLC from a Catalan company that is Industrial Shields. And what we do in this case is to connect the standalone through this IoT device who is provided by the supplier. And in this case, we get, again, all the information from the sensors and PLC from this machine. And also they needed a real-time dashboard to check the productivity and also the machine condition monitoring, okay? The same, we get this device as a gateway to get in all this data information, and we send it to the cloud, okay? These applications, these three first applications, are based on real-time monitoring and also diagnosis of the machine status. The third one, it's related. It's very similar, but in this case, the architecture changes because we have used an E1 IoT, industrial IoT router, okay? We get the information from an industrial robotic cell, also the parameters of process and production, and through this industrial component that it's provided by E1, we get all the information from the cells and sensors, and we send it to the cloud. And then we provide a dashboard with information of the productivity and also trends on the changes on the variables. So these three first projects are related again to machine condition monitoring, OEE to get the optimization of the production, and also fault detections through detecting alarms or problems in the process. This fourth example is a bit different. In this case, we had a machine that is intended to print images in a cork from a bottle of wine, okay, for marketing and commercial purposes. And what we have done here is to interact in a more low level. So we interact directly with the sensors. There's a machine with a marking header, and what we do is to interact with the sensors of this header. In this case, we have digital sensors, and also we control drivers from small servo motors in order to control in real time the process of marking this cork, okay? In this case, the architecture is that we have a PC that get the image that we want to print, okay? And we have to translate all this information to send it in a PCB board that is this one that is controlling in real time through an FPGA all the motors and also the laser who is marking this cork. Okay, so in this case, what we use the sensors not for monitoring is an example of how we use this information from the sensors to control a process of marking in this case, okay? And also all the information that we have from the status indicators, we send it through a cloud in order that the customer can also monitorize the production. Okay. This will be more on the side of Industry 4.0. And the last example I have is from artificial intelligence applied to test. As I said, we are not experts on AI. So what we do is to collaborate with a startup of the UPC, the University Polytechnical of Catalonia, because what we do, we have a customer in a railway sector, and what we do there is to test batteries, okay? Because there are some kind of trains that go through rural zones, and they also have power from batteries. In this case, our customer has concrete need because they test a lot of different systems from batteries, and they need to classify somehow these results. So what we do is, together with a partnership with this startup, we get the information directly from the sensors to get the state of charge and from voltage, resistance, and intensity from the batteries. And the experts on AI, what they do is to develop an algorithm to do a multivariable analysis in order to classify these batteries, detecting failures and also the balancing of these components. So what we do is to get information from from the machine, from the test, and we perform the test of the batteries at different levels because they have modules, and also they pack these modules until they get a battery pack completely. And with all the variables that we get from the test, we prepared all this information with considering timing and formats of all this data to deliver it as an input from the algorithm for artificial intelligence. And what the algorithm do is to classify and characterize these multivariable elements and get the KPIs to get the differences of each component. And at the end, as a summary of this project that also has the support from the government of Catalonia, what we have done is to make this analysis multivariable in order that our final customer can see the dispersion between the batteries and the product that they provide, in order to optimize how the customer pack these different models of batteries to get products that are more balanced and better in terms of efficiency. So the idea is not only test, use the AI to give an added value to the results of this test. And I think it's the last. So thank you for your attention. And if you have questions at the end of the presentations, I'm here, happy to answer.
Okay, thank you very much for your presentation, Martha. Now we are going to open the discussion section. If anybody has question from any presentation, you can ask. Hello.
Okay, if you don't mind, I will start. So,
yes.
Justino, I like very much your presentation. This application on TinyML.
Thanks.
I was just wondering about the result, the successful identification of the number.
Yeah.
I'm a little confused because sometimes it seems to be about 90% and others were much lower. Can you clarify?
Yeah. So the results showed that the model detects for YOLO, it detects very well for some numbers because some numbers clearly visible, but for instance, number 5 is half cut. It's still detectable because the numbers are shifted, right, in the training set. But the probability is low. It's only 6% of probability of the object detected in this place. So normally the cut detection is 50%, but we decrease this cut threshold. We put it higher, so lower. So in this way, we were able to detect the object properly. But for the first one, for FOMA model, it was different. This model, vice versa, it detects very well with high probability, but it detects also many objects. And so you have to cut objects which are not really numbers. In this way, we apply this threshold of 50%. So you kind of play with the thresholding in order to define what is the best threshold for this particular case.
And one question related to the results: have you compared the accuracy of the models that have you obtained in for I think you talk about an ESP32, and have you compared how will be the results with another hard with a computer with full capability of processing?
In terms of time, right? I want to compare both models on the same metrics, but I think it's a next step because I also use different metrics for FOMO. I use different metrics for YOLO, and then you cannot compare them based on the different metrics. Ideally, you have to provide the same metrics for the models and then to give information which model is better in terms of accuracy.
Yeah,
but
I want. I was not asking about comparing the time processing, but the accuracy of the final processing.
Yes, so I use here for YOLO, I use mean average precision, but for edge impulse, FOMO, I use precision and recall, and those metrics are different. So ideally, I have to converge them and then put them into the table in order to tell which model is better. But this is next step, which I didn't do yet. But thank you for this nice outline. Thanks. Stop sharing. And I'm also turning with the questions to Radu Boncia. I hope it's correctly pronounced. So my question, what is the best in terms of accuracy method for pathfinding in your robot and the pathfinding problem?
Can you repeat, please? The question I didn't hear.
What is the best in terms of accuracy method for pathfinding in your problem of pathfinding and robot pathfinding dilemma?
Okay, so basically for pathfinding, there are some certain algorithms like Monte Carlo and so on, or AlphaStar. There is a correlation between the inertial the sensor that measures the inertia. So the input for the algorithm is its current position and the movement, and there's the map that it's a LiDAR map created, which is a matrix, and basically going from an element in the cell in the matrix to another element in the cell, considering the what LiDAR discover, it's just Monte Carlo. So we are using Monte Carlo, if that's what you ask.
Okay, so Monte Carlo is the most efficient, or did you just apply because it's the best defined by previous
for
researchers?
So in robotics, for SLAM tasks, Monte Carlo is the best. Now, if the robot has to explore different paths, there's also an algorithm called AlphaStar.
Yes, A-Star, our robotic team use A-Star. So
yes,
maybe you could compare with A-Star pathfinding.
We are also using A-Star, but just when it needs to explore more paths.
So the best is Monte Carlo.
It's the fastest, the fastest to explore.
Okay, thanks.
I also had a question for, if I'm allowed, for Raivo. Raivo. So I will have a question because that's quite interesting, that part with the students learning, exploring actually a remote execution on microcontrollers. And my question is there significant difference that you have observed between students working in online environment versus an emulator versus a physical one? Are there any decline in students' performance or any problems that you have observed?
Yeah, to be honest, we haven't really done this kind of comparison in terms of students, let's say, performance or how well they acquire the knowledge. But I think there are definitely pros and cons for both of the solutions. So it's much easier to expand the virtual environment. It's just adding computing power, and then you can copy basically how many you really need those instances, but it's not that simple with real hardware. But I think that the feeling that you're really controlling the real hardware, you can see on the video that something maybe gets stuck. Let's say motor doesn't turn in the first place, or there is some other small things that the feeling what you get that you're really executing it on the real hardware, it's what makes difference. If it's nicely simulated, so that there is so many around you, like this, I don't know, AI generated images, or everything is very, very nice, and it's maybe not that motivating anymore. That if everything works, and even it's visually very nice, but it's still visualized or a simulated environment. But in real life, there is things sometimes down. You may have a correct code, but still doesn't work. And then you have to investigate, okay, what's the issue? And then maybe it turns out that it was actually the hardware fault. And that's also important knowledge that it doesn't mean that if the software is all well written, correct, then it always works. So in real life, it's not like this. And you have to be aware of that. There are more layers in communication, also the physical layer, and the bug or error can be anywhere. And usually it's actually maybe it is actually in other side. Of course, you can have also logical error, but more than 50 cases the error is in the other side. And that's definitely the important knowledge, I think, what the student don't get if they deal only with simulated environments. But yes, we haven't measured or done kind of scientific research to student performance.
Okay, thanks.
I have a question to Professor Radu regarding your presentation. I saw you used reinforcement learning as well, reinforcement learning technique. Am I audible? Please turn on your mic.
So you're asking about reinforced learning in robotics in our scenario?
Yes. Have you tested that technique as well?
Yeah. Okay. So we are starting with the reinforced learning. We haven't progressed that much because most of the reinforced learning is done now in NVIDIA Isaac Sim, and we haven't created let's say a perfect, not perfect, but anyway, a very consistent model for Isaac of our robot. We are still working because if you have something wrong, for instance, we have to model the IMU, the inertial measure unit, and we have an IMU that we haven't found on Isaac Sim as a device, as an asset. So we have to create an asset for IMU in NVIDIA, and there we have some problems. So we pretended that we have a different IMU, but it's not working. So in Isaac Sim, you can train like 100 agents in the same time, each one learning, for instance, to navigate. So we have for navigation, and we also experiment with the gripper. So it's a robotic arm that we want to mount on the robot and to learn the movements without programmatically program the robot to move. So this is where we use reinforced learning. Basically, it's a trial and error until it figures out. When it figures out, we save the model and then we put it on the robot. Not on the robot, because the robot, it's quite energy constrained. We put it on a laptop or a server, and the server dictates the robot what to do.
And so you shown the video of your simulation. It was a real-time test?
Yes, that was real time, yes.
Which technique you used for that simulation?
For that, it's Gazebo.
Gazebo, okay. In Gazebo simulator, you tested your algorithm, right?
Yes, but in Gazebo, we cannot run reinforced learning or large simulations. It's more like playing with standard robotics like localization, pathfinding, and so on.
Okay, thank you. So any other person?
If no one else has a question, I would like to ask one. It's a very general one, but I'm hoping that the experts that are with us today would be willing to offer their personal perspective. So I am asking about the trends that you believe will cut the industry a little bit, maybe unprepared, and will conduct to the needs of retraining the people that are working in the industry. So feel free to share your own perspective over this matter. It's probably there are a lot of things that will evolve and will make us to work on being better.
So if I'm allowed, I think one trend, I mean, not trend, but a very disruptive thing that could be coming in quite near future is this part of data fusion from large sensor networks, because it's just now that we have the capability to automate certain things like data analysis. And well, I think there is a huge potential for this part, like deploying large sensor networks and ensuring maintenance of large sensor networks, detection errors in the network, and of course, being very large, they have to be energy constrained. So this part of optimization is something that it will become very important in the future. Like we have this project with on earth sciences, that we have CO2 and methane gas detectors, and for energy we use solar panels, but of course solar panels, small solar panels, but the solar panels and the battery that we are using, okay, they could cover like a week, and so we decided to reduce the sampling, to send every 1 minute, every 2 minutes. So this is dynamically done, but then it's still not enough. So we come to the conclusion, for instance, that we need a separate node, a LoRa node, that communicates with all the nodes, with all the sensors, and makes prediction of the weather. So this node, which is powered from the grid and has some edge computing capabilities, would dictate the other sensors to adjust the frequency. So I think this is an area where there will be a lot of potential in the future, because we can do that now. Before, like 3 years ago, it wasn't possible to imagine this kind of thing. Thanks.
Thank you for your answer. I don't know, maybe anyone else that want to offer their thoughts on this matter?
Oh, no. I asked, not related to what you pointed out, I asked some other questions which I wrote while I watched presentations, and I think I got some answers about SP32 and okay.
You can ask again if you I don't know if you have other details that you need clarification.
Yeah, it was about Lucian. Okay, the project from Romania and sensors tracking people while on the traffic. So I was interested what type of sensors were used for this purpose. I saw web cameras, right?
Yeah, well, Raspberry Pi cameras, based cameras,
and
I think FaceNet or something like that is not done by me, the system, but like a model, and it's a system that processes every, I don't know, every 30 frames from each camera, and it's do a biometric identification.
Okay, localization probably sensors also, right?
For localization, no, for
only cameras.
Only cameras to know where a person is.
Okay, okay, clear. All right.
They might do some geolocalizations on their mobile phones because they are a telephone provider.
So it's only on web cameras, is it the project, or other sensors like tracking based on the sensors for location-based tracking, or?
We can get in touch with them to ask them more detailed, because at the moment I don't have this info.
Oh, right. Okay, I get it. Okay. Oh, and then the second question was to Raivo Cell about ASP32, because we also use them. Why they are so popular? And the answer is, I got the answer written, so I will read.
Comment. They are, of course, they are quite cheap, and
Okay.
of course, this development platform is free for everyone, compilers and a lot of examples. But they are also quite powerful in terms of their size. So they are very tiny. For example, if you compare with Arduino or others, they are much smaller. They have built-in Wi-Fi, Bluetooth, especially 32. So they are really multifunctional, small and tiny. It's easy to do this development. For example, we use them also the IoT courses, even the older version, which is ESP 8266, which is enough in terms of power because you don't need much power. But specifically, they are so small. For example, they also have a kind of standardized platforms like T1 Mini, which you can have a lot of shields on top of that, a bit like Arduino concept, but they are 4 times smaller, so they fit much better to IoT than the bigger one like Raspberry and Arduino and other things.
Okay, thanks. They are not faulty, because in my experience, they sometimes have this problems of stopping working suddenly.
Yeah, there are many versions. I mean, I think they have evolved. So even like in this 8266, there are several iterations of versions. So maybe the earlier one had some flaws, but you can always build the software with kind of like watchdogs and things. So we haven't had many problems. Sometimes there are like working several months and in some reason it stopped, but every controller can have this, and if you want to do some experimental work, not, let's say, directly industrial solution, which have to work in harsh environments, then it's fine.
Okay, thanks.
I also have a question. How safe are these devices? We want to integrate those, but it is really safe to give them internet?
I think there is the question of what kind of cryptography you apply for your communication. So you can have just a simple like MQTT, pure text communication, but if you need more safety so that the data cannot be manipulated or let's say stole, so it's the data itself is critical, then of course you have to have apply some cryptos. I think there may be not enough memory for encryption, but you can also then add some additional chips that help to that. I can't say for sure, but I remember that we had some issues that that was a bit lack of memory or some parameters was a bit weak for encrypting the communication. But on the other hand, if you're just measuring temperature or some parameters, then it's not that critical if data is stolen, let's say. But all the IoT system, what you build, you have to think of cybersecurity vertically through all the layers in the like data collection layer, edge computing, middleware. So there are so many layers that all must be secured unless the full system is compromised. So it's not only the one end, but it always the question that what's your ultimate purpose and where they're using it. So for educational use, I think they are very good, and also for prototyping, even industrial prototyping, you want to just test that this concept works, and then so you can save quite a lot.
I guess in terms of cybersecurity, we need standardization, or maybe some producers that are safe. I know that some are made in China. How safe are those? Can you control the firmware? Are we really sure that they send only to us?
Yeah, the question is what's the firmware, but you, of course, in microcontrollers, the firmware is what you upload over there. I think this is more, let's say the question is more if there's more sophisticated chips. Those simple ones actually are not able to have this functionality that they collect or process some data and then sending to China or somewhere else, because they're just too cheap for that.
The question was more for the IoT devices, which are complex.
Yeah, I think it's more like, for example, there is questions about solar inverters and things like this, which makes sense a bit to collect this data. But if you have very simple $5 microcontroller measuring the temperature, what can you do with this data? So
we had cases where servers had dual chips, and they noticed strange behaviors after measuring the power. So this is just an example.
Yeah, like I'm saying, it's more case for the much more complex, let's say, devices than this small microcontroller.
I have one more general question. So just to maybe this could be a last question, just to be sure that we get in time. Maybe you can tell us what new tools, platforms, technologies related to IoT you have encountered recently that are new to you, and how comfortable you are feeling, you feel to use them.
Okay, maybe I can a little bit comment. I don't have specific tools what I can refer at the moment, but what I think definitely, again, let's say in educational domain is that what comes is this AI-powered coding, so that, for example, you don't need any more, or we just reconsidering our teaching, that do we need to teach how to program those microcontrollers, for example, or rather incorporate this LLM tools, Claude or Copilot or whatever, which generates the quite good code for the microcontrollers, and of course this will have another challenges or threats, but the point is that we actually have quite redefined how we teach, what we teach, how to use those new tools. And of course, it's not only the case for the IoT and microcontrollers, but more general and specifically, I think, for the programming and software development, which gets quite rapid or distributed times at the moment. And this definitely also affects the IoT development.
Do we have additional thoughts on what Professor Raivo said?
A tool, for instance, that we have discovered, well, not recently, but it has gained quite a momentum. It's, for instance, Tasmota. We are using it a lot for firmware, for developing the firmware. Generally, we made the firmware ourselves, but for very fast prototyping, and it covers a lot of scenarios, we use Tasmota. So basically, it's a must now to use Tasmota.
For example, it also works well with this ESP controllers, so that you can take some Chinese, like son of ready-made, let's say, IoT device, which actually consists of ESP32, and then you reflash with the firmware with the Tasmota. And then you have your own firmware, but Chinese device, but with your own firmware, and it's open source. So you can be sure that there is nothing to be sent to the Chinese servers anymore.
Yeah.
Okay, I guess if no one else wants to add something, we can end the workshop here. I hope that everyone had a good tech day and a good and a productive workshop where you could address the topics that are in your interest. Thank you very much for being here with us today. And as you know, or if you don't know, you find out now, Merit Workshop organizes this type of workshops on AI, cybersecurity, and IoT. So this is just the first one for this year. If you are willing to participate to the next event, just check a little bit our website, and we will be very happy to have you with us. Otherwise, I wish you a very productive and good week, and I'm hoping to see you in future in more activities, and maybe to create some connections that would allow us to put the basis for future collaborations. I wish you a very good day.
Thank you.
Thank you. Thank you. Thank you very much.
Have a nice day.
Bye.
Thank
Bye.
you.
Thank you.
Have a nice
Bye.
day.
Bye.
Bye.
Thank you. Bye-bye.